Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 1, Lesson 2, Quadratic Functions, I Rule. A little bit of positive self-talk. It's always nice. The first section for assigned problems consists of the ready section. And the directions say rewrite each expression as the product of two binomials. That is our goal. And we're given a little bit of additional explanation here, which is nice. Each expression involves two multiplication problems separated by a plus or minus sign. Each multiplication problem contains a matching binomial factor that can be factored out so that the expression becomes, once again, a product of two binomials. So looking at the example that they provided, our example is 3x times 4x plus 1 plus 2 times 4x plus 1. And you can see that the matching binomial factor in this case is 4x plus 1. That appears in both terms, both the first term and the second term. So what we can do is we can factor that out, 4x plus 1, and then we take each of the remaining terms and those form the second binomial. And what that does is that gives us our product of two binomials. So, let's look at the first assigned problem, which was number 2. So for number 2, our question says 8x times x plus 1 plus 2 times x plus 1. We want to write this as a product of two binomials. The matching binomial factor in this case is x plus 1 and x plus 1. And so when I factor that out, I start with what I'm factoring, what is common, which is x plus 1. And then my second binomial is what's left over in my first term and in my second term. So in my first term, the piece that's left over is 8x. And then the piece that's left over in the second term is plus 2. It's positive because it says plus 2, not minus 2. And that is my final answer. Now, that is our final answer. This next part is extra, so if you want to skip it, feel free. However, if we were asked to factor this expression completely, which again is not what we were asked to do, but if we were asked to do that, we're actually not quite done, and the reason is because the second binomial has a common factor of 2 that we can also factor out. So if we factor out that 2 from the second binomial, we can just kind of slap it on the front right there, and then the x plus 1 is unchanged. But then my second binomial, because I factored out a 2, I want to divide each of those terms by 2, giving me 4x plus 1. And that would be the fully factored form of this expression. And again, the directions did not say to do that, so we're good with our original answer. But if you did notice that our second binomial here had a common factor of 2, good job, gold star. Next question is number 3. And again, we can see that they have a common binomial of x minus 10. So we are going to factor that out. Then we're going to look at our first term and our second term and our second binomial in the answer is going to consist of sort of what's left over. So in the first term, we're left over with a 6x. And in the second term, and again, notice it's being subtracted, so you want to say minus 1, because of that minus that's in front of the 1. And that is our final answer. Moving on to the set section. The directions here say, in each set of 3 functions, one will be linear, one will be exponential, and one will be a quadratic function. Explain the nature of change for the function, and find an explicit and recursive equation for each. So the first assigned problem here was 9b. And we have a table here on the left with a series of inputs that are x, a series of outputs that are f of x. And first thing we need to do is we need to figure out what type of function is this. So in order to figure out the type of function, we're going to want to look at the first differences. So going from 36 to 49, we're going to add 13. Going from 49 to 64, we add 15. 64 to 81, we add 17, and 81 to 100, we add 19. Now, right off the bat, we're able to eliminate linear functions, because if this was a linear function, we would expect this to be the same number each time. So definitely not linear. However, they are increasing by a linear amount, 13, 15, 17, 19. So there's definitely a pattern there. And if we go one step further and look at the second differences, so 13 to 15, we add 2. 15 to 17, we add 2. 17 to 19, we add 2. And so we see that there's a common, or rather there's a constant for our second difference. So between the fact that we have a linear pattern in our first difference and a constant in our second difference, that tells us that this type of function is a quadratic. So this is a quadratic function, and then to describe the nature of the change, well, like we just said, it has a linear rate of change, and an equivalent thing to say is that, or it has a constant second difference. Those two things kind of imply each other. And so the nature of the change is that it changes by different amounts each time. 13, 15, 17, 19, etc. Now, for an explicit equation, again, we're using function notation. So f of x equals, and as a reminder, an explicit equation is in terms of the input itself, which in this case is x. So we're looking for some sort of an equation involving x. As we saw in the lesson, one of the takeaways is that a quadratic function will have an x squared in it. And let's see where that puts us. So if x equals 6, if we want f of 6, well, it's saying take your input and square it. Well, 6 squared is 36. And that is, in fact, exactly what we see in the first line here. When we plug in a 6, we get a 36. When we plug in a 7, so f of 7, currently our explicit equation says to square that, and 7 squared is in fact 49. 8 squared is 64, 9 squared is 81, 10 squared is 100. And so we kind of lucked out with this problem because our explicit equation is actually the parent function for quadratics. It's about the most basic, actually, sorry, it is the most basic possible quadratic function. It's literally just f of x equals x squared. You take your input and you square it. So that is our explicit equation. And then for our recursive equation, again, f of x, because we're using function notation here, A recursive equation, again as a reminder, it refers to a previous term in the function. So it's saying, all right, well, in order to get the next term, you look at the previous term and then you essentially modify it in some way. So f of x equals the previous term, f of x minus 1. Now, as we saw in lesson 1, in a recursive quadratic function, what we want to do is we want to start by adding the constant second difference, which in this case was 2, times x, times your input. Now, we're not done because there's some piece here that we still need to figure out. There's some constant that we need to sort of verify. And in order to finish out this problem, what we want to do is we want to look at any two consecutive terms here. So we might as well just go ahead and start with the first two here. So what this table says is that you plug in a 6, you get a 36. You plug in a 7, you get a 49. So our recursive equation, if we let x equals 7, let's just say x equals 7. Well, then what we have is we have f of 7 equals f of, well, 7 minus 1 is 6, plus 2 times, now x, now remember, we're letting x equal 7, so this becomes a 7 here. And then again, we still have this sort of like missing piece. Now, if you take a look at our table, we know what f of 7 is. F of 7 is 49. So we can say 49 equals f of 6, well, f of 6 is 36. It's right there. So 36 plus 2 times 7 is 14. And really, we should assign a variable here to our missing thing. So we'll just call it d. And then plus d. It's the thing that we're missing. Well, this is relatively straightforward. We have 49 equals 36 plus 14 is 50 plus d. Subtract 50, subtract 50, and we end up getting negative 1 equals d. And so what that means is we can now finish out our recursive equation because our final piece is that we have to subtract 1 off of that. That's sort of the, like I said, the missing piece that we had to find. Now with a recursive equation, because a recursive equation is constantly referring to a previous term, we need a starting point, right? We need a sort of an initial term. And we might as well, in this case, because we don't have f of 1, we'll just go ahead and start with the lowest input, which was 6. We just need to explicitly state that, oh, by the way, f of 6 is 36. That's our starting spot. And then we could determine f of 7, f of 8, and just continue from there. So that's our final answer. The recursive equation is f of x equals f of x minus 1 plus 2x minus 1, and f of 6 equals 36. Okay. Next question was 9c. So again, we want to figure out what type of function this is, and in order to do that, it's a good idea to look at the first difference. So 11 to 13, we add 2, 13 to 15, we add 2, 15 to 17, we add 2, 17 to 19, we add 2. And as we just saw in the previous question, when your first difference is a constant, like it is here, that tells us that we have a linear function. So this is a linear function, and the nature of the change is that it has a slope of 2. Remember, slope means rate of change, and you can see here that the rate of change for each term is in fact 2. So the nature of the change is that it has a slope of 2. For an explicit equation, we have f of x. And again, with an explicit equation, we are looking for something that is in terms of x. There we go. So with a linear function, linear functions can commonly, I'll just do this over here on the side. So a linear function, we're looking for something like f of x equals mx plus b. This, of course, is very similar to y equals mx plus b. Essentially, these are saying the same thing, except the second one, the one that we're using is using function notation. So we're looking for something like mx plus b. Well, m is our slope, which we just identified is 2. X is our input. And then we're looking for b. Now, b, you might recall, is the y-intercept. Now, we're not really graphing this, so we're not, looking for visually the y-intercept. But what we are looking for is we're looking for some term that's going to make this true. So, again, if we take a look at, let's say, our first input here, this says that when you plug in a 6, you should get an 11. So what that tells us is that this result of 11 comes from 2 times our input, which in this specific case happens to be 6. And then, let me redo that 6. Okay. And then there's some other value b here that we don't yet know. However, we do know that 2 times 6 is 12. And we end up getting -1 equals b. That's the second time we got -1. That's kind of a coincidence, so please don't think that we're always going to get a -1. But we do, in fact, get a -1 again. So that tells us that our explicit equation is f of x equals 2x minus 1. And if you wanted to, you could go through and check that. If you plug in a 7, 2 times 7 is 14, minus 1 is 13, which we have right there. If you plug in an 8, 2 times 8 is 16, minus 1 is 15, right there, and so on and so forth. So you're more than welcome to double check that. For a recursive equation, f of x equals our previous term, so f of x minus 1, whatever term came before that, and then we're going to modify that in some way, right? Well, if you take a look at our first 2 entries in the table, notice that when our input goes from 6 to 7, our output goes from 11 to 13. So the question becomes, well, what do we need to do to 11 to get 13? Well, we need to add 2. We already identified that. So our recursive equation is actually relatively straightforward. All we need to do in order to get f of x is we take the term that came before it, f of x minus 1, and simply add 2 to it. Oof. Try it again. Plus 2. There we go. And that'll work, right? So, you could pick any pair here. It doesn't really matter. You could say, 9 and 10. So f of 10, which is 19, is f of 9, which is 17 plus 2. 17 plus 2 is 19. And again, with a recursive equation, because it's constantly referring to something that happened before it, you do need a starting point. And again, we're not given f of 1, so we'll go with the next best thing, that's available to us, which is f of 6. And f of 6 happens to be 11. Just establishing sort of where we're starting. You always need to do that with a recursive equation. And that is our answer. All right, 9D. We are looking for, again, what type of function is this? We'll look at the first difference. To go from -17 to -12, we add, why is the rig's being annoying today? We add 5. -12 to -7, we add 5. -7 to -2, add 5. -2 to 3, add 5. So we can see, once again, that we have a constant for our first difference. And as we saw in the previous problem, that tells us that we, once again, have a linear function. So we have a linear function, and the rate of change is that we have a slope of 5 this time. That's our rate of change. For our explicit equation, f of x is, with a linear function, it's going to be mx plus b. M is our slope, which we just found, so that's going to be 5x. Now, we could solve this like we did C, and we could solve for what our b value is by just picking one of these entries and solving for b, just like we did in part C. However, what's nice with this problem is that they actually give us what happens when you plug in a 0. So when you plug in a 0 here, you get a -7. And the reason why that's helpful is because when you plug in a 0, your result is the y-intercept. If you think about what a graph looks like on the coordinate plane, you have some function. Well, when x equals 0, sorry, that was a bad example. Get rid of that line. Let's go there. When you plug in a 0, you are on the x-axis. Bam, you're right there. So the fact that they're telling us that, look, when you plug in a 0, you get a -7. Well, that's great, because that tells us that our y-intercept is in fact -7, and we don't have to do any algebra at all. So that's nice. So that's our explicit equation. Our recursive equation, f of x, and as we've now seen several times, with a recursive equation, it refers to a previous term, so f of x minus 1, the term that came right before it. And just like we saw in part C, with a linear function, all we need to do to our previous term is simply add the slope. That's what slope means. That's the rate of change. And so because our slope is 5, we can just say, all right, we'll take your previous term, add 5 to it, and that will give you your next term, f of x. And as always, with a recursive equation, we need a starting point. Now, in this case, we could really list any one of these 5 entries, but because they tell us f of 1, we might as well go with that, because we normally will start with a 1. So in this case, f of 1 equals -2. Now, if you chose a different pair as your sort of starting point, if you said, f of -2 is -17, that's fine. But just please note that because we are given 1, we might as well use it. Our next problem is number 10. Directions say, graph the functions from the tables in problems 9 and 10, although really just referring to 9. Add any additional characteristics you notice from the graph. Now the directions here say place the axes so that you can show all 5 points. We are not going to do that. So go ahead and cross that out as well. Identify your scale, write the explicit equation above the graph. All right, so first assigned problem was B. For part B, the explicit equation was f of x equals x squared. Now, in order to graph this, oh, wait, here we go. So, in order to graph this, we're going to have our x-axis. We are going to have our y-axis. And we need to identify a scale here. We'll go ahead and use just a scale of 1. So we have 1, 2, 3, -1, -2, -3. Now, our explicit equation says that in order to graph this, or rather in order to get a table of values, you simply take any input and you square it. So when we plug in a 0, 0 squared is 0, and so our first point is actually at the origin itself. A little hard to see, but it is, in fact, right where our axes intercept, because when we plug in a 0, we get a 0. Oh, I forgot to establish the vertical scale. Our vertical scale, we'll also use 1. 1, 2, 3, 4, 5, 6, 7, 8. All right. So now getting back to plotting our points. Going to the right, when we plug in a 1, when x is 1, well, 1 squared is 1, and so our next point is going to be right there. When we plug in a 2, f of 2 is 2 squared, which is 4. So we plug in a 2, we get a 4, which is up there. And when we plug in a 3, 3 squared is 9, which is really just right on the edge of our coordinate plane here. If we go to the left, when we have -1, well, -1 squared, -1 times -1 is positive 1. So it is, in fact, positive. Quick note on the calculator here. If you try to do -1 squared like this, you will get the incorrect answer. I see students make this all the time. If you want -1 squared and you type it in like this, the calculator is going to give you the wrong answer. And the reason is that the calculator does the squaring first, then makes it negative. That is not what you want. What you want is you want -1 times -1. That's what it means to square something, and so you want to get a 1. In order to do this using the exponent, what you need to do is you need to make sure that your base is in parentheses like this, then square it. So you get what you want, which is a positive 1. So, just a little side note there. Getting back to our graph, if we plug in a -2, -2 times -2 is positive 4, which is right there. And if we plug in a -3, -3 times -3 is positive 9, which is right there. And now to finish out our graph, we just connect these. Just like that. I don't think, let me just double check the directions here. Graph, add any additional characteristics, identify the scale, explicit equation. That's it. So that is our answer for B. Going on to C, our explicit equation for C was f of x equals 2x minus 1. get a couple of axes here. Now for this linear function, I'm going to make my axes a bit more centered because we are going to be dealing with some negative values here. Okay, so those are our coordinate axes. And again, our scale, we can just go with 1. I'm not going to label all the numbers, so we'll just go ahead and say 1 and 1 and -1 and -1. Okay. So there's a couple of different ways that we can graph this. Our y-intercept is -1, so that's kind of a freebie. We might as well start with that one. So -1 is right there. Now, in order to get our other points, we could plug in values. We could plug in 1, 2, 3, -1, -2, etc. With a linear function, our slope is 2. So that means that from our y-intercept, we can actually generate a whole bunch of other points. If we want to go to the right, our slope is positive. So what that means is we're going to go up and to the right. So our slope is 2. So from our y-intercept, we can go up 2 and over 1, which means our next point is right there at 1, 1. Now, to verify that, if you want to go back to your equation and plug in a 1, f of 1 is going to be 2 times 1, which is 2, and 2 minus 1 is 1. So you can also calculate that point, not just move from the y-intercept. So there's really a couple different ways that we could finish out this problem. But in my opinion, I think using the slope method is probably a little bit easier. So now from this point 1, 1, if we go up 2 and over 1, that gets us to there, which is 2, 3. And if we do it again, up 2 over 1, we're right there, which is 3, 5. We could also, from our y-intercept, go to the left. Now, with a positive slope, if we go to the left, we have to go down. So from our y-intercept, if we go down 2 and to the left 1, that brings us down there, which is -1, -3. And if we continue this pattern and we do it one more time, we're down there, which is -2, -5. And then all we need to do is we need to connect these. And I'll just do it freehand. Try it again. And I believe that is everything. Last part of this question was part D. Our explicit equation from D was f of x is 5x minus 7. And again, we will include some axes here. There's our x-axis. There's our y-axis. And this time, it's going to be pretty similar to C. The only little wrinkle is the fact that if we want to plot our y-intercept, well, if our scale is 1 box, we're going to run out of space because from the origin, we only have 1, 2, 3, 4, 5 boxes to work with. So this time, it'll make our scale 2. So go down, this is actually going to be -2. And we'll keep the same scale in all dimensions. So this will be +2, this will be +2, and this will be -2. So each box is worth 2. Our y-intercept is -7. So -2, -4, -6, -7 is right there-ish. Let me do that again. Right, 2, 4, oh wait, 2, 4, 6, it's right there. There we go. All right. Now, from here, we want to, I think probably the best thing for us to do at this point is, well, we can still use the same idea of going up 5 and over 1. I think that'll probably still be the easiest way to finish out this problem. So right now, we are at -7. And our slope is 5, which means in order to get our next point, we can go up 5 and over 1. But please don't forget that our scale, we've established that each box is worth 2. So what that means is if we're at -7 and we go up 5, that's going to bring us over to this -2, and we go over and we're going to be at +1, which means our next point is right there. Because we're at our x value is +1 and our y value is -2. If we do it again, if we go from -2, if we go up 5, that brings us to +3, and we go to the right, that brings us to +2, which puts us right there. If we do it one more time, it should fit. And so from 3, if we go up 5, that brings us to 8, and then over 1 brings us to +3, which is right there. And when we connect these, we should expect to see a relatively straight line. Oh, that's nice. It actually made it a line. Just try to fix it a little bit. Oh, now it's going to be difficult. So let's just try that one more time, freehand. Okay. And that is our graph. The last set of problems in this assignment were in the Go section, and our directions here say find the greatest common factor, or GCF, for the given values. And the first question that we're going to look at is number 13. So we are looking for the GCF of 18 and 54. Well, what we want to do is we want to identify the factors that comprise each of these numbers and then sort of see what do they have in common. So with 18, what are the factors that go into 18? Now, if you are not super comfortable at finding the factors, you can use the calculator to sort of try, all right, well, does 2 go into it? Does 3 go into it? Does 5 go into it? I'm not going to show all the calculator steps, but if you would like some assistance in sort of figuring out how to use the calculator in order to help you with this, I would encourage you to come to office hours and we can discuss. So with 18, for 18 is even, which means there is at least a single 2 that goes into 18. If you divide out a 2 from 18, you're left with 9. Now there's no more 2's, but since we're left with a 9, you have not 1 3, but you actually have 2 3's. So this is easy enough to check. 2 times 3 is 6, and times 3 is 18. So this is the prime factorization of 18. 2 times 3 times 3, which sometimes you'll see this written as, I'll do this in red, sometimes you'll see this written as 2 times 3 squared, which is fine. Obviously, these are the same thing, but we're going to leave it as individual we're not going to use exponents in this context. So I'll just go ahead and erase that because we're not going to be writing it in that form for this specific problem. We're going to do the same thing with 54. So again, we want the prime factorization of 54. Well, again, 54 is even, so you know that there's at least a single 2. Every single even number has at least a single 2 as a factor. Nice place to start. So you divide out a 2 from 54 and you have 27. Well, 27's odd, so there's no more 2's. However, 27 can be written as 3 times 3 times 3. And again, this is easy enough to check. 2 times 3 is 6, 6 times 3 is 18, and 18 times 3 is 54. So we have found the prime factorization for each of these numbers, and the GCF is going to be, what do they have in common? Well, they have a 2 in common, they have a 3 in common, and they have another 3 in common, which means our GCF is 2 times 3 times 3. That's what they have in common. Now, you don't want to leave your answer like this. You actually do want to evaluate this or simplify it and get an actual answer. 2 times 3 is 6, and 6 times 3 is 18. That happens sometimes. Sometimes the GCF is in fact one of the numbers. The reason why the GCF here is 18 is because any number is a factor of itself. So 18 is a factor of 18. And with 54, you can write 54 as 18 times 3. So both of these numbers have an 18 in them. And clearly that's the GCF because there's no number that's larger than 18 that's going to go into 18. So that is our GCF for number 13. The next assigned problem was 14. So again, for 14, we're looking at 14 and 21. So again, we want to find the prime factorization. So for 14, 14 is even, so it starts with a 2. You divide out a 2 and you get a 7. Well, 7 is prime, so you can't break that down anymore. So 14 is just 2 times 7. 21, well, 21's odd, so there's no 2's. So the next factor up from 2 is 3, and 3 does go evenly into 21, and then you're left with, again, a 7. And 7 is prime, so you can't break it down. So that's it. That's our prime factorization. And we look for, all right, well, what do they have in common? And what they have in common is a 7. So for number 14, our GCF is, drum roll, 7. And that is our answer. Last question assigned in this lesson was number 16, and for 16 we are looking for the GCF of 45 and 36. Again, we're going to find the prime factorization. 45 is odd, so it does not have a 2. Next factor is 3, and there is a 3 in 45 that does go in evenly. If you take your calculator and do 45 divided by 3, you should get an integer. That tells you that 3 is a factor. The integer that you get is a 15. You have to continue to break down a 15. 15 also has a 3 in it. And when you divide a 3 out from 15, you're left with a 5. And 5 is prime, and so that means you are done with 45. For 36, 36 is even, so you know that there's at least a single 2. When you divide a 2 out of 36, you get 18, and again, 18 is even, so there's another 2. When you divide a 2 out from 18, you're left with 9. 9 is odd. However, 9 can be expressed as 3 times 3. You're welcome to check all of this, but the numbers should work out. So now again, we say, all right, what do they have in common? So we have a single 3 right there. We have another 3 right there. And that is all that they have in common. Therefore, our GCF is going to be 3 times 3, which hopefully you know is 9.